Oh, okay. I've started the recording.
All right, John.
Yeah, I mean, I did submit a pull request, basically trying to explain the bandwidth requirements. If you need to do potentially like 6 state updates per connection, and try to explain the need for it to be reliable, for those state updates to be reliable. I think it's kind of like maybe putting the cart before the horse a little bit, because in some sense, like, we really should be showing like what are the states and what are the updates that need to be made. And then I think it would be clearer to understand like why like those state updates need to be reliable. But I believe that that if you make the state updates reliable, it solves some problems, particularly, with making sure that connections are closed, and also making sure that like active connections aren't like aged out of the other DPU inadvertently. So anyway, if you accept the premise that the state synchronization messages should use a reliable transport, then the question becomes, well, what should that reliable transport be? And I think like one obvious answer is, well, why don't we just use TCP? And we could, and I think that would be an okay answer. But one of the things I'm trying to point out is that the bandwidth is so high that I don't think that there should be any expectation that a single TCP connection for state synchronization will be used for the state updates. Also, if you think about the fact that there might be multiple physical ports on a DPU, you wouldn't want the state updates to all go through the same physical port. You would want the state updates to be balanced across all of the physical ports, so that you're not like stealing the bandwidth just from one port to do the state updates. So for that reason as well, it seems that the transport of state synchronization updates needs to be multiple parallel streams between the two DPUs. And so that's really kind of the point of what's in this document. And then sort of the second part of the document is, if you think TCP is kind of too heavyweight for this, the sort of operating conditions under which Dash is operating, where the two DPUs are kind of localized, they're near each other. There's like the latency between them is pretty low. The number of switch hops maybe is low, and that the network is already like pretty reliable, but not 100% reliable. Then like under those conditions, like there may be like a simpler reliable transport protocol that can be implemented on top of UDP. And so there's a description of something that is simpler than TCP. But I think that that's kind of a secondary thing. I think the primary thing is just the acceptance that that the transport for state synchronization needs to be reliable, and that it needs to use multiple parallel streams between the DPUs. I think like if there was agreement on that, then I think it's like a secondary, it's sort of a secondary matter as to like, well, what is the appropriate transport?
Yeah, so I think those two are, we can separate them. First of all, dividing connection into streams can be solved separately.
Yep.
But then the question, if we need the reliable connection or reliable transport, I don't really agree with that for the reason that we are trying to solve for real-time data, and we cannot really guarantee, like TCP guarantees for the static data, to not lose any connections. So it's either we are losing the current connections, or we are losing the connections that will be open in the future while we catch up with the window.
So, right. So let me try to address that. I believe that the entire system has to be engineered to provision for enough bandwidth and priority potentially and dedicated buffering or whatever is necessary to not have the path between the DPUs for state synchronization be the limit of your connection rate performance. However, in some events where you're not able to synchronize state because you're getting drops or you're not getting enough throughput through those streams between the two DPUs, I think that you have to mitigate that by dropping packets that are data packets that are arriving on the DPU. And maybe you don't have to drop packets for like established connections, but I think you would at a minimum drop packets for like SYN packets for like new connections that are like trying to start up. That's kind of, in my mind, like the only mitigation for not being able to synchronize the state. Because I think if you do the opposite, if you say, okay, I never want to drop like data packets arriving at the DPU, regardless of whether I can synchronize state or not, I think that you end up with like broken state. And that broken state means that that you've lost your HA ability.
Right, but for how long will it be broken? So simple example, we have like usual topology that we are looking at is two TORs for high availability on the TOR level, and then each DPU is connected with one port to one of those TORs. Meaning that if we want to synchronize two DPUs, one of them the state synchronization messages will go from one DPU to the TOR to another DPU.
Right.
What if a link goes down between the TOR and the backup DPU?
If that
I'm trying to understand how will reliable protocol help with that.
No, in that scenario, I would call that a failure scenario. And in that scenario, one of the DPUs should be elected as the, like single available DPU, and all traffic, data plane traffic, should be directed to that DPU. If the synchronization link goes down, that's as much of a failure as a DPU failing or
I disagree with that, because it's a common thing to have link flapping. Link can be down for, I don't know, 1 second. Do you want to declare a whole DPU down, or do you want to cache, like according to this document, it's like, what was that, 12 gigabit per second bandwidth, which
well,
is
I was estimating that 5 million connections per second would require
Okay.
12 gigabits per second of state
Okay.
synchronization.
Yeah, which means that every second we transport like how much? 1.5 gig.
Yeah.
So if the link goes down for 1 second, do you want to cache 1.5 gig of data on the primary DPU so that you can retransmit that?
Well, there's one of two things you can do, Marion. You can not cache, 1.5 gig to retransmit it. Of course, the window here is very small. You only need a very small window for retransmit. What you would do in this scenario is you would either fail over, or if you didn't want to fail over, you would drop all new SYN packets. So there would be a period potentially of like 1 second where you're dropping new SYN packets.
I don't really understand why we would be so radical to drop the SYN packets if we cannot synchronize. Yeah, we know that we have our state desynchronized, so we cannot do failover for some time until we will catch up with all the like periodic updates. Because even if something happens, we still have the periodic updates, which will eventually synchronize the state. So why would we want to sacrifice new connections for
How
a
often
temporary?
are you doing those periodic updates? I think you have to think that all the way through. I mean, if you have millions of flows, you're going to do periodic updates for millions of flows at what rate? I mean, that is more. I mean, any single flow. How often would its periodic update be in that case?
1 second, 2 seconds, we can pick a number.
Okay. Well,
because if you have a long-lived connections, how else would you know not to time it out on the backup?
so on the long-lived connections, Marion, the periodic rate for updating long-lived connections just has to be at like the time, like has to be like around the same as the timeout rate of the connection. You just have to be like a little bit faster than the timeout rate of the connection to keep it alive on both DPUs, right? And like, we're talking about like 4 minutes or something like that as like the timeout for like a TCP connection. But if you're saying like, no, like I want to just be able to like resynchronize the state of every single connection every 1 second, that doesn't scale. I mean, like this is like 64 million flows like per 200 gig of throughput. Like that would use a lot more than the 12 gigabits per second to do that.
Where's 64 million coming from? I don't really get that.
Those are numbers that I think Gerald has been.
Yeah, but okay. So then, okay, let's stay with that premise. We don't want to do periodic updates. Fine. But then again, we have a limited window, and the port goes down for 1 second. Usual thing, link flaps.
Why is there a link flap? This is like a very engineered path between the two DPUs.
No, sorry, I won't accept such a premise that link does not flap in the data center. At any point, link can flap. This is a common thing. We are not doing. We don't have a soldered connection between those two guys. The link can flap between any 2 points.
So, okay.
Sometimes it's in the optical box that they have to go through. Sometimes the technicians are performing maintenance and they bump wires, or I have seen a lot of link flaps in our data centers.
Okay, but what we're talking about here is, let's talk about a smart switch, okay? And you could talk about like that the backup is remote or whatever, but like let's just talk about like the normal operation. 2 smart switches with like a physical point-to-point link between the 2 smart switches. And that physical point-to-point link between those 2 smart switches is there for the purpose of this HA path, okay? So the link flap you're talking about is like between two like co-located switches with a dedicated point-to-point link. Okay, let's say, you know, for, I don't know, there is a link flap on there and it's a very short period of time. I think the answer to that is that the DPUs drop SYN packets during that period of link flap. I think that that's the answer. I think if the link is deemed to be broken, then I think you have to declare one DPU the master and switch all
Right.
traffic to it.
So this is Bud.
But
A related scenario is if the link is flat, link flaps, link goes down. If there are asymmetrical flows, and say like a SYN packet arrives, and that's supposed to put an entry in the flow table and open an entry in the reverse direction. If there's no connection between the two DPUs, then that reverse connection won't be opened. So it's not like you can say.
that's not really the point. There is, so even in the, if you look at the topology, you have two links from the DPU. Even if one flaps, eventually BGP will redirect you to the other one. It
But
will take.
those are the data plane. That's like the link to the data plane. Where this is like the link between the two DPUs, like the HA link.
So again, you cannot assume you have a dedicated HA link. HA goes on, most likely goes on the same ports that the data.
I think that this is an unsolvable problem if you're not willing to accept that there's like an engineered connection between the two DPUs. I mean, maybe you can accept like a very small like link outage time without like failing over to one or the other. But I think it's like unrealistic to assume that there's going to be like unbounded periods of time where that link is like unusable and that somehow you're going to still keep these two DPUs running like independently. I mean, it's like you will lose like the synchronization state. And
that's my point. If you want to keep it ideally replicated, then you will end up in a situation that you can very easily lose it. And it's not something out of
Mary,
the blue.
I'm afraid that the solution of just like periodically updating the state is like it solves it. The periodically updating the state at like the flow timeout rate is okay. That's like minutes, but periodically updating the state every 1 second because a link might have flapped, I think is like, if you do the math on that, like the bandwidth that you're going to need is more than the bandwidth of the DPU. You can't copy the entire like flow table state in 1 second.
What do you mean? It's like, how can it be more than the bandwidth of DPU if in the worst case scenario, let's take the worst case scenario, we would just mirror every flagged TCP packet. It's not more than DPU bandwidth, and adding to that periodic updates.
Just think about the periodic update of 64
Okay.
64 million flows, or pick a number, right?
Yeah, 64 million flows. How much can we pack into one message?
Well, let's just, how often are you going to like send a periodic update for a given connection?
So whatever number we will pick, 1 second, 10 seconds.
All right, pick 1 second.
Okay.
That's 64 million messages per second.
Not messages, it's flow updates. How many flow updates can we pack within one message?
Well, I'm calling messages, and then you can pack multiple of them into a packet.
Okay, I understand what you mean. So we can pack multiple messages into the packet. So according to what you have in the paper, how many messages can we pack into the
Let's say 60 for IPv4, right?
60?
Is this
So
helping at
it's
all? Did I display
yeah.
it
So
while we
it's
talk?
roughly
Okay.
1 million PPS for
Okay.
periodic updates.
Okay, but like, let's say that like are you doing in addition to periodic updates, are you also doing like event-based updates, or is it all
Of course.
periodic?
You will need event-based to be to cover the
Right.
to
Right.
not have to be synchronized to lesser amount of time. We do not want to be a backup to be 1 second
Right.
behind.
So like let's say you're doing event-based updates. That's like maybe another like million packets per second.
Yes.
Okay, so you've doubled like the amount of messages in this approach. And Marion, like one of the issues here is not just like what's the bandwidth of the messages, but you actually have to process those messages. Like if you're getting a periodic update, you don't know that periodic update is like needed or not needed, right? So the only thing the receiver of that periodic update can do is to treat it as if it's a real update. And you have to go into your flow table, you have to like do the actual work of the update. So like you're like using a lot more bandwidth, and you're using a lot more like DPU resources to deal with like the periodic updates. And like all of this goes away if you accept the premise that you'll use a reliable transport.
Yeah, but again, I can easily break that. Just if you have a link flapped for more than your window allows, which is really not a lot. So how much do you estimate the window size to be?
As Bud pointed out, if you have a link flap for like more than 1 second or 2 seconds,
I'm talking about the short one. I'm talking about the really short one, which is quite common.
okay, I mean, in the really short one, I mean that the same thing would happen in both. If you have like a short link flap, right? You will like in the one case, like let's say SYN packets are coming in, and you're processing those SYN packets, and those event-driven messages are now being dropped because of the link flap, right? Well, okay, now the link flap goes away, okay, and the ACK packets come on the other direction on the other DPU, okay. Those ACK packets will be dropped because the synchronization didn't occur. Okay, and it will take like 1 second for that synchronization to happen, and then I guess the ACK packet in the other direction will work. Okay, if you take the reliable transport approach, you don't have to buffer. You could decide like how much buffer you're going to have for very short link flaps, but like you don't have to buffer more than the window size. And if if the link flaps and the window fills, then you start dropping SYN packets, and it has the same net result, which is like the new connection is not opened up until you can get the state reliably synchronized.
Okay, yeah, so the same net result. Okay, fine. But then I will ask you this time, give me the size of the window. What is the expected window size? What's the number?
Yeah, I mean, I think the expected window size is small. I mean, I think it could be, like these packets are large. I think that this window size could be, 128 packets, let's say.
$128 packets is just, it's kind of like I don't know, it's a link flap of a time, I don't know, one. Even if we have a link flap for 1 millisecond, we won't be able to accommodate for that. And what
Right.
happens next? Do we declare it down?
Well, I mean, I think that's a decision that we have to make. Like, at what point do you declare a link flap like a failure of the link? Okay, that's like an independent decision.
Yeah, but you won't be able to cache for 1 millisecond of link down.
We don't. What we'll do is we will flow control, and the flow control will cause us to not generate new state update messages. And the way that you not generate new state update messages is to basically drop packets that would have caused state updates.
And how does primary know not to generate state update messages anymore? Because it doesn't know that the link is down. It's not
There's a flow control. There's a window. Once the window is full, then you can stop putting new messages into the buffer. Okay.
So hold on, but then does it mean that we receive ACK for every flow synchronization message that we
No.
know that? How
No.
do we know that
So
that we should stop?
how do you know that what?
So imagine that the primary sends flow sync updates to the backup.
Yeah,
And
I mean, I imagine more this is like active, but okay, let's just go.
yeah, but for every flow there is one that received the SYN and will send
Sure.
an update.
Okay.
Yeah, so that's the prime.
Okay.
It goes to the Tor. From the Tor, it goes to the backup. And link between the Tor and the backup goes down. Primary doesn't know that the link went down. What will happen next? Like, how will it stop in time?
So, okay, so what will happen is that the sender, okay, and like, there's senders, there's transmitters in both directions, but like what will happen is the transmitter will send up to the window size and not have received an acknowledgement. Okay, and once that happens, then.
But hold on, you said that there is no acknowledgement. Am I missing something?
The reliable transport protocol has acknowledgements.
For every packet?
The acknowledgements don't have to be for every packet, but the acknowledgements have to be at least like, as frequent as your round trip time. They don't have to be for every packet. But generally, Marion, like there will be packets flowing in both directions, like synchronization packets will be flowing in both directions, just because like you said, some connections originate on one DPU, some connections originate on the other DPU. And so like there's kind of, let's just say, a balance between like each DPU sending state synchronization messages to the other DPU. And the acknowledgements like piggyback off of those data packets. So like you'll have acknowledgements, you'll have data and you'll have acknowledgements like continuously flowing in both directions. And again, we don't have to use this protocol. This like maybe is simpler than TCP, but like it could be TCP.
Yeah, but this TCP suffers the same problem. Well, not really the same problem. TCP cannot withstand that because it's so my point is that reliable transport requires you to have an end-to-end flow control. You don't really have end-to-end flow control. Eventually, we end up with the same thing. You are dropping new connections that are incoming that you cannot accommodate for. Because you cannot go back to the VM and say, please pause your application.
No, but Marion, like we never go to the VM and say pause your application, right? But if
well,
you
we
think,
do actually. If you take like really lossless end-to-end protocols like RDMA. That's what they do. They pause the application until they can transfer all the data.
So Marion, like regardless of HA, completely independent of HA, each VM will have a connection per second rate, right? That's been provisioned for that VM. Okay.
Yeah.
What happens when the VM exceeds that connection per second rate? How do we tell the VM that to stop new connections? We don't.
That's completely different. That's what the customer paid for. If the customer paid for less CPS, they won't receive more.
Okay, and how do you tell the VM to like stop?
Is that via metering or the counters or the metering
You
buckets?
Right,
you don't have to
drop
tell
SYN
the
packets.
VMs.
We'll
Hold
drop
on,
SYN packets from that VM.
Yeah,
That's right.
yeah, but you don't have to tell the VM that VM is breaking the rules. Here, VM is not breaking any rules. It's your problem.
The VM's not breaking any rules, but you can always drop a SYN packet in the network, right?
As well as any other TCP packet, and
You
it
can-
will be retransmitted.
That's right. And so in this like, scenario of like, there's some very short link flap on the transport between the two DPUs, it's effectively the same as if you dropped a SYN packet in the network. And it'll get retransmitted and the VM will get exactly as many connections per second as they paid for.
Yeah, but the difference is that difference goes down to the implementation. So probably that's why, because up till now only I was asking questions. Maybe other vendors want to put their 2 cents. I'm not sure if the end result is the same. What is the preferable way for the implementation in the hardware? Because for me, it is much simpler to have a stateless implementation and lossy, as opposed to what is proposed here, to keep a window to retransmit. This seems to be, from the implementation standpoint, much more complicated. If we agree that the end result is the same, in case if we have a link flap longer than the window size.
Right. So Marion, I think like you're saying, okay, it's much simpler to just do this stateless thing. Like I think the counter to that is like it doubles the bandwidth between the two DPUs potentially. Okay. And I don't think it actually is simpler in the sense that it uses like twice as much DPU resource to handle these like periodic messages that like 99.9999% of the time like weren't necessary. So the DPU is like handling them, processing them, not knowing whether like it is a real state update or it's just reflecting like the state it already has. So
we can talk about the periodic updates if we really need them, or if we lose a packet or a few packets, what will really happen then? Can we resynchronize only those without really doing retransmissions? That's also a valid question.
I think the periodic messages is like another form of a reliable messaging, except that like it's not like selective to only send the messages that like needed to be resent. It's sending all flows over and over and over again. I mean, that's like the difference.
But how will you then synchronize long-living flows?
So
how will you update them, rather?
Okay. So let's say you have a long-lived flow. Let's say you get to the established state. Okay. Now let's say the established state has a 4-minute age idle timeout. Okay.
Why 4? But okay, never mind.
I think 4 was a number that has been talked about in the past as like, this is what Azure currently has. I don't know. If there's a better number to use than 4 minutes, that's fine. But let's just say it's 4 minutes. Okay. What you would do is like, you would send an update to your peer like sometime before that 4-minute expires. Okay, like if the flow is still active on your local DPU, you wouldn't keep updating, your peer like to say, oh, I'm still active, I'm still active, I'm still active. You know that your peer is not going to time out that flow for 4 minutes. So as long as you update your peer, let's say after 3 minutes and 58 seconds to say, hey, this flow is still active, that's like enough for the peer to like add an additional 4 minutes of timeout to the peer. So like you do need to have periodic updates, but only at the idle timeout rate. They don't need to be at like a 1 second rate.
But okay. You still need to somehow pick exactly those, which is not clear to me. But then going back to original argument, if we're saying that we have, let me put it right, we have, well, let's stay with the 4 minutes timeout. If we would put periodic updates to 10 seconds, it makes our primary and backup or sender receiver be out of sync for at most 10 seconds, which reduces or in other word ratio to the periodic updates to the newly opened connections will be 1 to 10, which we have 10 seconds every 10 seconds periodic updates, which reduces bandwidth for periodic updates to 1/10 of bandwidth for the event-based notifications. And still, I believe this will be much simpler to implement than keeping state in the hardware.
So, Marion, I started to ask this question earlier about how asymmetric flows are handled in the event of the HA link going down. I mean, so say a SYN packet comes in and it can't be transmitted to the peer. And the reverse flow is that SYN ACK is going to arrive on that peer. Like, how does that work?
Yeah, so eventually you will, with the periodic updates, you will catch up.
So the SYN ACK will be dropped, right? I mean, assume, and then it'll get retransmitted, and then retransmitted, and eventually.
Yeah, because everything is retransmitted.
Yeah, and so say if you
Unlike UDP, interesting question. I didn't think what happens to UDP because I don't really know the use cases for UDP, but yeah.
Okay, so if the synchronization messages between the two peers, say you retransmit everything every 10 seconds, then after 10 seconds, the peer's flow table gets populated. The ACK is being continuously retransmitted by the remote host. And then eventually the SYN ACK comes in, sees the flow tables populated, and then the connection continues. Is that the idea?
Mm-hmm. So if the link goes down in any case, I think we can agree here that some packets, some portions of the flows will be dropped. For me, a much worse trade-off would be to try to implement this kind of like a state machine with a window and retransmissions. Plus, I don't really see how it's gonna work. Okay, we're saying that we will receive X, and we can say that for some time, if we're not receiving an EC, we will start dropping even faster, even before the link goes down and we understand what was happening. I can understand that, but still, I see a big problem with this implementation. I don't know how we can really maintain all this in the hardware.
Well, that seems like it might be a limitation of your hardware. I mean, it's you know, I think if you just if it just look at like the bandwidth, you look at like how quickly you get back to a synchronized state, and you look at how much like DPU resource it takes to handle updates. Like the reliable transport is like more efficient on all of those. If the issue is that you just can't implement a reliable transport, I mean, I don't know what to say.
Well,
I don't think that I really there is. I'm looking at it as a cost benefit scenario because we will solve for 0.001% of traffic in the network or less, and won't really gain much of it, because even in your proposal, you're saying all the time that the network is engineered well, we don't really have any losses, except from what I can think of, which could be common, like first one would be link flap, second would be buffers. Because we're still going through the Tor, or in case of smart switch through T1 most likely. So you may have buffers clogged up.
Again, I mean, you know, the amount of bandwidth and the amount of events and synchronization that's going through this path is very high. Like the processing load of the synchronization messages is like almost as high as the data packets, right? And
No.
what do you mean no?
As I
I
said,
mean,
so even according to your calculations, it's like 10, 12 gigabit per second for event-based messages.
yeah, I know, but I'm talking about like you know, flow table like updates, you know, like, you know, doing a lookup in the flow table and updating the state, right? You know, you're getting data packets and you're doing lookups in the flow table and you're updating the state based on you know, the flags and stuff in the packets. Like the HA, like state updates are generating like a very large number of like load in terms of like flow table lookups and updates. And I would say it's like, you know, it's equivalent load to like the load on the flow table from the data packets. Because it's symmetrical, right? Or you know, or in some cases asymmetrical, like the two directions of the flow are on two different DPUs, and so like it's just you're getting as much state update from your peer as you're getting like from your locally arriving packet.
Yeah.
Okay, so like the HA is like a big source of work that has to be performed, right? And you know, in with like this is like so fine grained of like state update that it's that you know, if you were architecting a product, you would say I just want a like dedicated link between like these two DPUs. And I
Again,
think
disagree. Doing some kind of like an MLog dedicated link type scenario, we cannot take this as an assumption.
Hey, John and Marian, this is Suresh. I think, you know, I'm from Fungible. maybe it's a good idea to chime in at this point. I agree with Marian that I don't, needing a dedicated link is feasible, but
I'm
I
not,
don't think that is a requirement though for a reliable transport to have for this control connection. I don't think we should have to insist on having a dedicated
I'm
link.
not insisting on a dedicated link. I'm just trying to draw the analogy to like, you're trying to create a dedicated link through the network topology between these two DPUs. Of course, it's lossy. Of course, it goes through switches. I understand that.
Yeah. No, my point is, I think that's the argument that throws off the whole theory. I am actually in the favor of creating a reliable connection between the DPUs for the state updates. And in terms of whether it should be a live update or an incremental update, that path is the same across between these two approaches, right? Should we update only incremental state? Or not, right? I mean, even in case of periodic update that Marian was proposing, I don't think it's updating every repeated connections, right? It's only the changes.
No, I think it's updating every single connection because it does not know whether the peer reliably received the previous update.
I see your point. Yeah, I think from a simplicity perspective, having a reliable connection between the DPUs and having live updates makes more sense to me. And it could even be TCP. Why to invent a new protocol?
Right. There is this, connections per second in the VM, and then there is flow add rate, and then we know that certain packets will be dropped. But the focus is for those flow entries that we have already added, we need to ensure HA works and to communicate and have that connection between the HA pair, that these are the connections that I am looking at, and these are the connection status, and that needs to be synchronized with the HA pair. I think that is important, and I mentioned that in the last meeting too, for the control messages. How it will be done, whether it needs a new protocol or it can piggyback with all the acts and do it in line as we add the state, but it has to be synchronized with the HA pair is my thought. I haven't gone through the PR from John, which I will do, and have some more comments for the next time. But some method to ensure that the flow entries that have been added and being tracked in one of the HA pairs to be communicated and synchronized and kept in complete alignment with the HA pair is important.
I think, guys, I think we're running out of time for this meeting. Would you all agree? Maybe we need to have some more discussion next week.
Probably, yeah. There was
Yeah.
still stuff that Gerald wanted to come back to
Mhm.
us with about
Right.
the DCMP case.
And he said he would come back with that next week. I mean, just to add a little bit of levity, can't we just lay a cable, the home run cable on the data center floor and just connect these two things? I'm just kidding. That'd make it easier. Like a direct connection.
Yeah, I'd love it.
Yeah.
I like that.
Yeah, let's just do that. I'm kidding. Great. Well, I think I captured a lot of notes, a lot of questions. I'll put it in my notepad for next time. I think, exploring both paths is it's a lot. But do you guys feel like we're at a good ending point for today?
Yeah, because I think we're just going to keep repeating the
Going
same
round
thing.
and round.
Yeah.
Mhm.
Maybe next time others can look at the proposal and other vendors and think and say what they think, because
Look at John's
I was
proposal.
yeah.
Okay.
I was
And I
talking
did
most
put
of the
it.
time. I didn't give
Yeah,
anyone.
I did put it in the chat window, but I'll send out an email to all of us with it, so that we all have it and can take. I was reading it while we were talking as well. So, okay, great. I'll send that out. And thank you, John and Bud, Marian, for all the work, and everyone for attending. And I'll give Gerald a summarization. I see him tonight at 7 o'clock. I'll give him a summarization of what we talked about.
Okay. Great.
Okay. I appreciate you guys. I'm gonna stop the recording and I'll post it in the YouTube channel.
Okay, thanks.
So it'll be there. Yeah, yeah.